Hello, welcome to today's tutorial. Today we're going to talk about the hexagon perforations with multiple points or curves to affect its patterns. Alright, let's start. So the first step we're doing is to introduce hexagon grid. Then the size will be 100. Extend will be 100. And then we have another 50 to the Y direction. And the plan, we're going to use the YZ plan instead of XY plan by default. So it looks like a wall. And then we're going to use scale. Connect the cells to geometry, and then we use area to find the center of each hexagon, and then connect the centroid to center as the scale center. And then we can use 0.8 for now, just to show the effect. So now our overall hexagon pattern is created. Then the next step, we're going to introduce multiple attractors to affect the overall size or each individual size of the hexagon. In tutorial 2, we introduce curve attractor. So today we're going to use points attractor, or using popular 2D. The input region will be a rectangular, which is actually the bound rectangular of all these hexagons. So we're going to type rectangular 2D, 2 points. Sorry, rectangular 2 points. Point A will be our the bottom left point. Connect centroid to list. Index 0. We need to flatten it. Then we find the bottom left. Then connect to point A. Then we copy, paste. Index will input -1 as our second point. Connect to point B again. Select bottom left and top right. Then the plan will be our YZ plan. So now you can see a rectangle is created. Then we connect the rectangle to our region. Apparently 100 points is too many. You only need 3 for now. Then we can also find an integer to affect the seed. We can adjust it to find the 3 points that we like. I think in this case 6 is my favorite. Then I'm going to use the 3 points to affect the size of all the hexagon. Similar to last tutorial, we need to find the distance. Let's show it again. We need to find distance between all this center of the hexagon to its closest point, right? And then we use this distance to affect the size of hexagon. So when it's closer to the closest point, the hexagon is bigger or smaller, and then it's far, it's different size. And then we only want one attractor to affect one point at the same time, because if the point is too close to that attractor, you don't want that point so far away to affect it. So we're going to find the distance between the 3 points to all the points. So need to connect that, connect it. It's the output at the moment is a tree type of data. We need to flatten it. We use point collector, and then right click flatten, connect the centroid here. So now we have 5,000 points. Then we have another 3 points. But if we directly connect it like that, the output is not what we want, because we're actually using a a list to calculate with another list. For example, we have 1, 2, 3, 4, 5 until 1000. Another list is only 1 and 2. If we use this list to multiply this list, it only works like 1 multiplied by 1, 2 multiplied by 2, 3 multiplied by 1, 4 multiplied by 2, 5 multiplied by 1, 6 by 2. So it's not really what we want. We need to make this as a tree list, right? And then that 1 can work with 1, 2. That 2 can work with 1, 2, right? So what we need to do is we need to graph the input. And now you can see the output. We have 5,000 branch, and each branch will have 3 numbers, right? That 3 numbers is actually, for example, that hexagon have 3 different numbers to 3 different points. And then we're going to sort list to find the closest point, distance between every single hexagon to its closest point. And then we list item. And then, as what we did last time, we need to remap all this distance to to a number that we want. Connect the value. We need to flatten this again, and then the source will be a bound domain, like that here, and the target will be 0 to 1 again. So all the distance are remapped to the 0 to 1. Then we introduce a graph mapper, which is Bezier again this time. And now we have 5,000 numbers. Be careful, but before we just connect it back here, we need to flatten all these inputs again, because that input is a tree. So when you use a tree, for example, we have a 5-number tree and then another 5-number tree. That's our tree, right? So each branch has one number, and when we multiply this tree by that tree, the way it works is 1 to 1, 2 by 2, 3 by 3. So it only works 5 times. But if we're using that tree, this tree, for example, to multiply a list, 1, 2, 3, 4, 5, right? That means that one will calculate with 1, 2, 3, 4, 5 times, and then that 2 another 5 times, that 3 another 5 times. In our case, we have 500 branch of tree to calculate 500 numbers in a list. That's really a lot of calculation, so we need to flatten everything to make it only calculate once. So we can use geometry here, flatten it, connect that here, and then remember to lock this over before we connect. Connect that, and then we connect that, and we unlock this over. If we only show here, you can see there is error here. That's because our output is 0 to 1. So we need to change into for example 0.2 to 1, because you can't scale to a geometry to 0, right? So now it's all working. We can actually give it multiple battery again, and give another, for example, 0.8 to affect that number again. Alright, so in that way we can use that 0.8 to control the overall size, and then we can use that graph mapper to adjust the gradient to point that we like, and then that 3 points, we can actually change it into 4 or 5 or 6 to influence, to have like many more attractor, point attractor. We can also change the seat, to change location of the attractor. So that is point attractor, and then we can also quickly talk about the curve attractor. So we can draw multiple curve here again. 1, 2, 3, and then we grab all this curve to grasshopper here, and then we find the distance from each hexagon to the curve. Is the battery we used before. Curve closest point. Connect all these points to our curve. Graph the input. So it's actually calculated with all the curves. And then we solve this. We can just directly connect that distance to here. So now you can see the curve is actually influence the hexagon pattern. And then if we change the shape of the curve, it actually influence the our overall pattern. After we get this pattern, let's hide all this curve for now. After we got all this pattern, what we can do next is to create a surface for realization. So we got all this geometry and all these guys. What we need to do is just to create a surface. Surface between the out hexagon to the internal hexagon. So we're using a merge here. Then we graph the input, connect that one here, connect that one here, and then we actually, by doing this, we create a tree, right? A 5,000 tree, and in each tree there are 2 numbers. It's because we only want that out hexagon to work with internal hexagon, and then we connect here. We got the pattern that we want, and then we can also extrude it, and the direction will be unit X. Then we can give it a distance. For example, we give it 10 mil. Here, direction, base. Yeah, this calculation will take a bit of time, and then we just bake it. Yes, please. And then we go to a pattern, give it a bit of material. Let's use orange, pink this time. Then we can visualize it. Cool, that's today's tutorial. Thank you. Thanks for watching today's tutorial. Please subscribe to support and check out my other videos.